Okay, so it's 1:31 already, so let's start. So yeah, everyone, thank you for attending this webinar, and yeah, welcome to another IDEA StatiCa webinar. So today I'll be showing you transfer wall design, which using Etabs, and then we will transfer it to IDEA StatiCa Detail for more detailed analysis. So my name is Stefano Kusumali. I'm a product engineer in IDEA StatiCa APAC, and I have about 5 years of experience working as a structural engineer, mainly designing building and infrastructure projects. So in GoToWebinar, you will be muted by default, but if you have any questions, please don't hesitate to use this GoToWebinar panel to type in your questions and click send. Then we will try to answer your questions. Right, so yeah, let's start with the new introduction of our new features, which is the Etabs beam link. So this features is released recently in the release of version 25.1. So if you haven't updated yet, please update to version 25.1 so that you can enjoy these new features. Okay, so before starting, I have this one poll. So this is the first poll. How do you design your transfer wall? We would like to hear about how you currently design your transfer wall and if there's anything that we need to improve on. So I just launched the poll. Okay, so it is in progress now. So yeah, if you haven't voted, please do vote in because we would like to hear about how are you currently doing the wall design, transfer wall design in particular, and if there's anything that we can improve in our software that we can better cater for you. Yeah, so I've seen a few people have voted. So yeah, those who haven't voted, yeah, please, we would like to hear what you think about this. Whether you're using hand calculation, strut and time model, or you check stresses in the global FEA software, or IDEA StatiCa Detail, or you don't normally design transfer wall. Right, I'll give it 10 seconds and then I'll just close the poll. Okay, cool. So yeah, there are some that have voted and I'll share the result. So basically 41% and 34%, 41% is using hand calculation, and on the second one is the 34% using check stresses in global FEA software. Yes, I think I also heard this is what commonly people use to design transfer wall. And next one is 20%, you don't design transfer wall. Okay, good. And just 5% of you is using IDEA StatiCa Detail. Okay, that's a quite interesting view. And yeah, I hope that today's webinar can change your view a bit and you can utilize IDEA StatiCa Detail for that. Right, let me reshare my screen. Sharing, yep, I think I'm sharing my screen. Okay, thanks everyone for participating in the poll. Right, so let's just start the webinar. Basically, IDEA StatiCa is comprised of combined into a two module, which is a steel module and a concrete module. On the steel module, you can see that there's our connection app, which is the most popular of our apps. We can also do anchoring and also frame design. And on the concrete side, we can design a wall, cross-section, beam with discontinuity, means with beam with opening, and beam with even opening and pre-stressing. And we can also do anchoring. But this is not everything that we can do. There are a lot more that we can do out of this. You can find out more in our website if you are interested. Right, so the first app, another app that I'm going to introduce for you is called IDEA StatiCa Checkbot. So what is this and why am I introducing this app to you? This app is basically a connector between your FEA or CAD software into IDEA StatiCa apps. So as you can see on the top left here, there are some FEA model that we are supported. some FEA software that we supported, Etabs, SAP 2000, SAP Pro, and so on. And below that, there's some CAD software that we are supported, but this is not all the software that we are supported. We support a lot more softwares. If you're interested, you can go to our website, ideastatica.com/BIM. So basically what checkbot does is it will import the structural analysis data from your FEA. Let's say you are coming from Etabs, right? So it will import your material, your geometry of the wall. It will import the forces, load combo, yeah, and so on. So and the thickness of your wall and all the information needed for design. It will store it inside checkbot, and then when you decide to export out of a checkbot to our detail application, basically, yeah, it will send all the data into our detail application. So this is what I'm going to show you today, the brand new Etabs BIM link, which uses Etabs, right? Because yeah, coming from Etabs, the global model, and then coming to our checkbot application, which I just mentioned in the previous slide, basically connecting Etabs and IDEA StatiCa. Then from checkbot, we will export it to our detail application for further analysis. But yeah, I just want to introduce this concept of a B and D region. Basically, B region is those region where the strain of the beam is linear, so that you can use those formulas inside the design code. But the D region is this discontinuity region or disturb region, basically where there's an opening, for example, where there's a concentrated force, like this corbel where change of sections. So this is called a D region, right? So in this region, you cannot actually just use those formulas you find in the design code. You have to use another method, let's say the famous strata and tie, of course, you can use that. And yeah, some other approach that you can think of. But basically, it is a more complex process. You would need trial and error and so on. Why did I talk about that? Because I want to emphasize on why we are creating this link between Etabs and IDEA StatiCa Detail. So it's because global FES software is good in overall analysis and B region, right? For example, you have a frame, you have a column, you have a beam. It's a very good, global FES software is very good in solving those design for those regions, but not in the actual detailed analysis and D region, right? For example, as you can see here, the coupling beam of two shear walls, but there's an opening in it. It is considered already as a D region, and I would say that the global FES software is not very good in designing this region. Next one, crack width is important, right? Because especially when you are dealing with those projects which quite stringent in the need to meet certain crack width limit, but there's no way currently to verify it in the global FES software. So if you're talking about Etabs, there's no way that you can see the crack width of a wall element, but yes, you can see the slab crack width, but not with the wall element. And lastly, we have heard from our customers as well, right? That the engineers wanted to do a detailed analysis of complex wall in IDEA StatiCa Detail, but there's no link yet back in the past, right? So they wanted a link so that it's the transfer of data from Etabs to IDEA StatiCa will be more seamless. And that's why we have decided to create this link. So what are the use cases for this Etabs link? Right, we can imagine, coupling beam with the openings. It'd be quite hard to solve in the global FES software. And you can imagine this wall with openings, so many openings. I think will be, quite impossible to solve in the global FEA. Maybe you can do with a strut and tie, but it will take quite a while. Then lastly, yeah, transfer wall with the opening as well. I think it'd be a quite complex case to solve. On top of that, we also have a use case from Mr. Jose Victor de Oliveira, which is one of our customer that verifies the needs of this link between Etabs and IDEA StatiCa Detail. So basically, he's interested in the behavior of this coupling beam and shear wall, where there's a change of section in the shear wall here. So what he did was, because he did this sort of project before we officially launched the link, he would have to model this geometry manually inside IDEA StatiCa Detail, and of course he would need to transfer all the loads, then all the load combo and all that manually in IDEA StatiCa Detail. But of course, after we launch this link, then we don't need to do that anymore to manually transfer the data anymore. Right, so that's all the introduction part. Now I'm jumping into a demonstration part. So yeah, okay. Before that, I would like to ask you one more poll regarding how do you calculate a crack width in your transfer or in your wall. Okay, so yeah, okay, now it's open. So yeah, what I would hear mostly is approximation using stress, or people normally for the region, they only design for ULS, or do you use IDEA StatiCa Detail, or do you use any other software? Yeah. So if you haven't voted, yeah, we would like to hear the feedback from you as well. Okay, start coming in. Okay, quite interesting. I'll give it 10 more seconds for people to vote. Okay, then I'll just close the poll and just to share with you the result that yes, this is what I heard as well. You know, most people would answer that they are approximating using stress to understand the crack width. Today I'll be showing you a better way of how to get your crack width out of your wall design. Okay, just hide it. Share my screen again. Okay, so jump into the demonstration part. Basically, I have this building. This is all regular building, but when it comes to this three column, right? When it comes to the lower level, there's a change in the layout. That's why they would need to have this transfer wall. Okay, so let's just open my Etabs. Okay, so this is the Etabs model. So as you can see here, yeah, this three column in particular needs to be removed on the lower floors because of the lobby requirement. For the lobby, they need a more open space. And then, as you can see here, I've run the analysis already. So I just go, so this is what we are particularly interested in, right? This particular transfer wall. So I'll just go to the elevation. Right, so yeah, this is how it looks like, right? Then let me just show you the stresses on the wall. For the ULS, I'm showing the minimum principal stresses, which is the maximum compression stress that you can see. Okay, just changing the range so you can see better. Right, so I think, yeah, I think it was this number 2. The answer for the first question would be to see the stresses on the global FEA analysis. Well, yeah, so this is how most people will do it as well after, the second choice after strut and tie, because strut and tie might take quite a while. So they would see the principal stresses of compression force, then I would say this area will be the most critical if we see the contour of the color. So if we zoom in over here, we wouldn't want to take this like this area, because this is a stress singularity area because there's a corner here. So I think the most sensible one would be to take the stress around here. Wait, let me just zoom it in so you guys can see. Okay, so around here, I would say engineering wise, we would say it's around 14.5 to 15, I guess. So if you are using, okay, let me just zoom out and yeah, just make it a little bit bigger. I'm not sure if it's a better, yeah, so it's around 14.5. So if you are just, referring to our FCK, let's say we are using a 30 MPa capacity of the concrete, and then we divide by the safety factor of 1.5, it comes out to be around 20 MPa lah, our capacity, right, based on stress alone. So I would say this wall thickness is still okay, right? It's still, you can still use this wall with this thickness, right, based on this. Well, because I'm not 100% sure, so what I will do now is I will bring it over to IDEA StatiCa Detail by using the new link. So what you need to do is just need to go to Tools and open our checkbot using the the plugin which is inside your IDEA StatiCa Detail installation folder, and then we will wait for our checkbot to open. It's opening on the other screen. I'll bring it in once it's fully open. Okay, it's opening, yep. Right, so normally people will choose steel because, yeah, most people will be designing the connection. But now you'll have to change to a project type of concrete. Then you can select your design code here and the national annex as well, if you decide so. Then you can click create project here. Right, so after you do this, it's a blank screen because yeah, you haven't imported anything. So what you want to do, you go back to Etabs, select the wall that you would like to import to IDEA StatiCa checkbot. Then just click on this wall button here. Right, so yeah, you can see here the wall has been imported and the thickness is imported as well, 350 mm thick, and also the material. And you can see here that all your load combination, the ULS and SLS combination also automatically transferred over. So what you want to do here, right, once you have this, you want to click on this detail button here, right? Then you select the wall that you want to create as a detail project. You select all and then you just right click. So then it will create a new detail project here. Then you can choose to whether you want to merge the wall or not. Basically, if you don't select merge of wall, then it will be split according to what you have in Etabs. But if you select a merge wall, then it will be merged automatically. So once you have this, you just right click on this button here and then click export to detail. Once you do that, you just save it as a detail project, click save, and then it will open our detail application. But before that, you can see that there are some out of plane forces shown here. Basically, it will just tell you that there are some out of plane forces which is not considered in our IDEA StatiCa Detail. Because yeah, our app is in 2D and most of the wall is normally would be designed in plane only. And we can give some modifier inside Etabs to actually redistribute the out of plane forces to the other walls. Right, so this is our detail application. So what do we have here? Of course, we have the wall. the thickness of the wall, the material of the wall, and then the openings that you have in Etabs. Then next you have this load cases. This is basically the forces that we have exported from Etabs. You can see here there are three large forces here. This is of course coming from the tree column. And you can also see there are small distributed forces here coming from the slabs. Same on the lower level here. And one more thing you notice here that we also import the sort of the reaction force coming from the wall below, because we would like the user, the engineer, to actually decide where they want to put the pin, the support itself. So they can, by doing this, we allow the engineers to decide where they want to put the support. What else do we have? We have these load combinations here, which is coming from Etabs, will be the same name as what you have set in Etabs. And yeah, so then we can start the analysis by putting in some rebar. Okay, so you just click this one, rebar assembly. I want to put a group of rebars. Yeah, and then you can just start putting in where you want it to be. Using the edge one, I want to put a vertical rebar from the bottom wall first. So I just do this. Then I put some anchorage length of 1 meter extension. Then I change the anchorage type because I change it to a continuous bar, because as you know, there's another wall below. Then yeah, I just change the number of layers and the number of bars in layers. And you can also change the distance, but for now it seems okay to me. Then I just copy it, want to change it, and I want to put it on the other side. The only thing that I change is the anchorage and the extension, and remove the extension on the bottom here. Next, I want to put the minimum rebar for the main transfer itself. Firstly, I want to put the horizontal bar first. Horizontal bar means you can see here that there's this master and edge. So the edge, we want to put an edge number 6 because I want the horizontal. So we just change this to number 6. Then I just want to remove all the extensions, and I want to move it down a little bit. So I will change this cover value here to say 100. Right, and then I want to change the distance to 400 mm. Yeah, something like that. Then I want to do the vertical bar for the transfer wall. So I change the edge to edge number 7. As you can see here, there's this edge number 7 notation. Okay, I change it like this, but then I want to change the distance to be a bit closer because this is a vertical rebar. And then I want to change the position so that it cuts right here. So how I do that, I change this apart from beginning, and I change to 6,000. Yeah, something like that. Right, so as you can see here, it's already quite crowded. You might not know which rebar you are working with. You can always hide the rebar by clicking this draw reinforcement button. Right, so I'm just going to hide it. Then yeah, just I think few more bars before we start the analysis. I want to do the horizontal bar for the bottom part. Again, change the edge. Sorry, edge number 8. I changed like that. Yeah, just I split it up a little bit. And I put it at the other side as well, which is edge number 4. Right, then I want to add 2 more rebar on the top here. Top, I changed to number 6. Right. Then I remove the anchorage. Then I move it down a little bit. The reason I'm putting this is because there's a slab here. And the slab, when they have a lateral force, a seismic force, there will be quite a lot of lateral tension force here. So that's why I put in this rebar. And then last one at the bottom of the transfer wall here, because yeah, as you can expect, if you have a transfer wall, then there'll be a lot of tension in this area. So I just change it to edge number 2 here. Edge number 2. Then I put some anchorage length on the left and the right side. Then I just change number of rebars, and I move down the bar a little bit. Okay, then I show all the rebars. So this is sort of the minimum reinforcement that that's needed to be put into our transfer wall. And yeah, that's it. We can one last thing is the support. As you can see here, the structure cannot be calculated yet. So you go here, I put a line support. Then you just change the edge that you want to support. I give a roller on the left side. And another one, a pin on the right side. Okay, so as you can see now, the warning is gone. You can start this, press this calculate button. But to save time, since we have quite a limited time in this webinar, so I've prepared the already run model. As you can see here, the first thing that you notice is this one here saying that the analysis cannot be completed. Basically, it's saying to you that the wall has failed. And if you observe here, the highest utilization ratio is in concrete. So means what is causing this transfer wall to fail is actually the concrete failure. But why is that? Haven't we confirmed that, seeing the principal stresses from Etabs just now, isn't it, 15, 14 MPa, which is still far from our limit, which is 20 MPa. Well, let me just get back to the slide. Yeah, so yeah, this is why actually when a concrete is under compression, right, then there'll be some transverse tensions, meaning it's a perpendicular to your principal stress. There'll be a transverse tension causing transverse crack. Then there's a less confinement for your concrete. If there's a less confinement, means there's a weaker compression capacity. This phenomenon is known as compression softening. Then you might ask, why is it considered in the code? Do we have to consider this based on code? The answer is yes. So if you see this in Euro code, right, if you are talking about, strut and tie and all that, actually there's this reduction factor of 0.6 on the strut. And on the node itself, there are some factor K2 and K3 based on the arrangement of the node. Same with the ACI. If you are using ACI, it'll be called as a beta instead of K. But it's the same thing, struts, interior struts, and then the nodal, if it's whether there are one ties or two ties, then there are different factor which accounts for compression softening. Inside IDEA StatiCa, it is automatically calculated. So you don't need to worry, or you don't need to be overly conservative by taking, let's say, 0.6 for all your design, which is super conservative. But in IDEA StatiCa, it is automatically calculated. Okay, let's just going back to IDEA StatiCa again, showing you the strength. Right, so just to confirm again, all right, this is 14.5, okay, which is similar to what we have in Etabs. But why is there a failure here? If we see this utilization, here is about 90 and 99.5%. So I mean the failure is actually happening in this strut. But as I say again, you see this value here is, well, it's still far from our limit. Why is it failing? you can refer to what, as I mentioned before, is a compression softening effect, which is automatically considered in IDEA StatiCa by this factor called KC2 factor. Right, so from the glance, right, you can see that here the factor is around 0.7, 0.75. So if you can imagine 0.75, right, if you times it to our capacity is 20, so it becomes 15 MPa, right? So that's exactly why this is failing, because if we consider the compression softening, we reduce the capacity of the concrete to 75% lah, based on our analysis. So that's why it is failing. So how do we fix the problem? Yeah, there are several ways, but the one that I'm going to do today is to actually just put another compression bar here so that the compression stresses inside the concrete can be distributed into into this new compression rebar. So as usual, we just add another group of rebar. Then I just change the diameter, change the location. I want to do it by 2 points, which means I need to decide the start and end. Something like this, but then I want to change the number of bar in layers, number of layers into 2. I want to change the distance to be a little bit more closer, so something like this. So hopefully, yeah, by doing this, I can make my wall pass. Okay, I prepared the already analyzed model as before. Let me just change to the other model. Yep, that's it. So as you can see on the top left here, that there are 3 green ticks, meaning for ULS, there's no more issue, right? So, well, our solution works. And yeah, as you can see here, there's no more failure here. I think it's about 95% of the capacity now for the concrete. But of course, we are interested if this rebar is actually taking compression or not. No worries, you can go to the reinforcement tab here and then change it to sigma S, which is the rebar stress. And as you can see, yes, in fact, yeah, this rebar is actually taking some compressions out of the concrete so that there's no more compression failure caused by the compression stress. So our solution works for ULS, but as you can see here, there's still some failure in the crack width and stress limitation. Let's solve the issue on crack width. First, we want to see where the crack width is failing. Right, so interesting, right? It's happening in the compression strut, right? So I guess some people are saying that they are using stress to estimate the crack width. But if we see the compression stress inside concrete, this is minus 8 MPa. You wouldn't check your crack here, right? You would check where there's no compression, where there's tension, basically. But on the compression area, you wouldn't check it. But then if we check the crack width, actually it is happening in this area, right? So I would say if you have used the stress to estimate your crack width, I would think that you would miss this crack width, failing crack width check lah. And this is happening again because of the, when you have a compression in the principal stress and transverse direction, there'll be some tension. We call it transverse tension. And to mitigate this, of course, the option is to add more horizontal rebar at this area. And I prepared a model which have more horizontal rebar in this area. Let me just show it to you. Okay, so then yeah, you see that there are more rebar in this area now. And as you can see now, there's no more failure on the crack width around here lah. Yeah, so it reduces to okay around 0.17 millimeter. And on the top left here, you can see that the crack width is actually within limit now, 99.9%. It's actually the failure of the crack width is now not the failure. The highest crack width is now here, but it is now within the limit. And regarding this one failure check, right, it's a stress limitation. You can go to this step here, stress limitation. Okay, just give me 1 second. Okay, so basically, as you can see, the failure, the stress limitation failure is actually happening on those corner, this corner. So I would categorize this as a stress singularity instead of stress concentration. Okay, so we just talk a little bit more about this. So what is this stress singularity, right? So stress singularity is common, is everywhere in the FEA solution lah. So all FEA will have this issue, what we call stress singularity lah, where there's a change in the section of the shell. Then you'll have what we call stress singularity, which is something that we can ignore because this is a problem in the FEA analysis itself. But on the other hand, if you see a stress concentration, this is something that we would need to take care of lah, because this is really what is going on in the structure. But stress singularity is the problem of the FEA method itself, so it's not really happening. But then how can you identify whether it's singularity or concentration? If it is singularity, if you make the mesh smaller, means a more detailed mesh, then you will have a higher stress value. It will keep going up until super high. If you keep making the mesh smaller, then you can identify that as a stress singularity. But if it's stress concentration, if you make the mesh more detailed, smaller, the value will be more or less the same. Then that's when you know you have a stress concentration and you need to take care of this issue. But since we know here is a stress singularity issue, it's in the corner, then we'll have this limited check option, which means we will turn off those stress singularity area, which is more than 100%. Then yeah, so I think that's it. We are satisfied with what we have with our rebar design. So we just go to this report tab here and just create a report which we can submit to our other parties. And just give it a few seconds. Okay, so this is how the report looks like. All the loads and including the load combo and yeah, the stresses, everything, the engineering report, and of course the crack width as well. But what is interesting here, right? You will get this bill of material included lah. So, well, I guess it can help you to communicate better when they want to start the construction. What is needed, the rebar needed in a very detailed manner, like the length, the width, and the number of items also listed to something like this. So I can imagine this is something that can help you in the manufacturing of the rebar, process of manufacturing of rebar. Right, so I think that's all from the demo. Right, I'm just going back to the presentation. So just a small summary, so yeah, based on the survey, I think engineers would design the wall based on the principal stress, but as you can see here, principal stresses is minus 14.5, FCD 20 MPa. Principal stress is still far from FCD, but is it really okay? Well, if you don't bring it to IDEA StatiCa, you wouldn't know that you would need the additional compression rebar to actually alleviate some of the compression stresses out of your concrete, because your concrete actually cannot pass or cannot take the compression stress. Then if you're using this link, right, how do you check if the force is okay or not? Because of course, as an engineer, you would want to make sure everything is correct. It is quite simple. You go to Etabs, you open this table called element joint forces shell, and then you'll see this table. Basically, we take this F1, F2, F3 into our IDEA StatiCa Detail. So basically, you can use this to confirm and to just to feel that you are doing it correct. And some recommendation if you are using this link. Meshing of the exported wall is important. We recommend you to go for smaller size, because as you can see on the left here, if you are not meshing it, you can see the concentration of force. And yeah, from engineering judgment already, you would know that this is wrong compared to the one on the right where the force is distributed equally. And if you have a frame connected to the wall, you just use a rigid link to ensure correct force distribution. If not, then it will be super concentrated into this one node, which is also not correct. And load cases with steps is not supported. You would need to explode into several load cases. So this is our recommendations if you want to try it or want to use this. Then last part of this presentation is verification, because we understand that safety is very important. Of course, in structural engineering, right, you would want your software to show the correct design result. But of course, we think that as very important as well. We are comparing the result with a real life experiment for cobble, D-beams, and shear wall with opening. Those D region which normally design using strut and tie method. And this is the result. The blue color is actually from the experiment. Green color is the strut and tie, and yellow color is from IDEA StatiCa Detail. For cobble, as you can see, our result is closer to real life, same as a deep beam, or is close to real life. As well as for the shear wall with opening, that our solution is actually closer to real life. And one thing that you can observe here, especially for shear walls with opening, that STM is super conservative, that you are putting in more material than it is needed, in my opinion. So yeah, you can start using our solution and you can have a closer result to real life. So just a summary. So why is it useful? Why is IDEA StatiCa Detail useful for you? First, it's a better design solution. As you can see, it can be used for both B and D region, but of course, it would be more useful in the D region, as you can see in the demonstration. Safe and accurate design, you don't need to worry about anymore. You don't need to estimate using stress in the global FEA model anymore. Just use this and be safe. And lastly, it's a save time, because if you're using strut and tie method, there'll be a lot of trial and error included. Next is the safe material. As I mentioned in the previous slide, our solution predicts the capacity which is much closer to reality. And as you can see, if you are using STM method, which is a well-known and great method, you'll be super conservative compared to the real-life experiment result. And lastly, use the link from Etabs to Detail, resulting in no data loss and no data error, which is very important in structural engineering. Okay, so last poll. Yeah. So I launched the last poll. How do you find this workflow, right? Whether it's very useful, whether it's useful, neutral, or no, you prefer to use hand calculation. We would like to hear your feedback so that we can adjust our solution to your needs. Whether we should improve this solution more to have more use cases, so that it can help you more, or whether you think this solution is not going to help you at all. Yeah, please help us with the with your thoughts so that we know where we should improve our solution. Thank you for those who have voted. I'll give it 10 seconds for those who haven't voted. We would really like to hear your feedback and see where we should improve our software. Okay, still coming in. Okay, thanks. So yeah, most of you have voted. Okay, so yeah, thanks for your feedback. I think 94% find it either very useful or useful. We are glad for that. Oh, sorry. Yeah. Sorry. Okay, so I have I've shown. Okay, I thought I've shown the result, but yeah, this is the result. So 94% of you think that it is either very useful or useful. We are grateful for that, and yeah, we are quite happy with the result. And thank you for your feedback, helping us with how we should deal with the future of our solution. Okay, thanks for that. Going back to the slide. Okay, just before the closing. So if you are interested in these features, right, please, upgrade or try out our version 25.1. You can scan this QR code. It'll bring you to our website. You can find 14 days trial over there. And this solution is available in the complete enterprise editions. And in the same website, you can also see there's a ask for quote if you are interested in the solution and would like to be connected into your local reseller or local office. And lastly, there's also a release note here for 25.1 if you are interested what updates that we bring in this latest version. So I'm just giving a few more seconds for you to scan to get to our website and get the 14 days trial. And yeah, get the chance to connect with the quote requests. And yep. And the next events, the last webinar that we have for this year will be on the 4th of December, which is the design of steel warehouses, where we will be showing you the capability of checkbot, how you can use it to automate your connection design to help you save your time with bug analysis. So join this webinar to see more. Okay, so comes to the end of my presentation. There's some Q&A which, yeah, maybe I can answer one or two. Yeah, so there's one question, can it be designed to AS 3600, which is the Australian code? Yes, we are fully supporting the Australian code. So we are supporting Euro code, Australian code, and ACI for the time being. And from Welfin, will you be able future design for diaphragm? Yeah, certainly it's a good idea. But yeah, you can use it currently, you can use it, but of course it wouldn't take into consideration your out of plane forces for the slab lah. But yeah, that's an interesting idea, and I've heard this from quite a lot of people. Maybe we can consider that in the future. And yeah, I think okay, it's from Nasim, right? Can IDEA StatiCa check bursting requirement? Well, The bursting requirement in the stride and tie is actually considered using those K factor that I've shown you, 0.6. And yeah, as I've shown you, right, our solution can actually calculate the K factor automatically so that you don't need to calculate the reduction factor yourself. Then yeah, last one I think from Wei Xiong. Can reinforcement be generated? Well, there's this. Okay, let me just. I think I just show you. There's this tool what we call typology optimization. Basically, this one can actually help you showing you where the tension and the compression is lah. But then for now, for the time being, right, you will still need to put in the rebar yourself based on these based on the stresses field which is shown. So you still need to put in the the rebar manually, but this result can help you with the with where to put the rebar. Okay, from Muhammad Al Rubai. Okay, last one. Can you use it for slab element? Well, as I mentioned, for now this is in plane solution. And yeah, as we all understand, slab element is mostly loaded out of plane lah. So mostly now is a fall wall, which is loaded normally in plane lah. Yeah. Okay, from Kwang Hu Nguyen. Okay, this is interesting. I want to answer it. Can we export reinforcement? Yes, we can, but currently we can export from DXF, which is from AutoCAD. Then we can import the lines into IDEA StatiCa Detail so that it can be used as a reinforcement. Yeah, I think it takes a while. Okay, I think that's all the question for today. And from Wei Xiong Chu, I think I'll contact you separately because yeah, this takes quite a while, I think. Okay, Ken, thank you very much, everyone, and see you on the next one.